So last time we went through this, we saw that there were certain times when we had to start a problem by taking the logarithm of both sides. But certainly we do not need to do that all the time. In fact, a lot of the time you wouldn't want to do that. And so taking a look at these 6 equations here, if I wanted to find the derivative of these, which ones of these would I in fact need to use logarithmic differentiation for? Let's go through them one by one. Let's start with this first one, y equals x to the power of x squared. Would I need to use logarithmic differentiation for that? Well, could you find the derivative any other way? I don't see a way here. That is, yes, an example of one where we would have to use logarithmic differentiation. All right, let's go sideways from there. So to the 3 to the power of 2x minus 1, would we need to use logarithmic differentiation on that one? Well, could you find the derivative without taking the log of both sides? Yeah, I think we could. Because we do know what the derivative of 3 to the power of x is, and so this would be a chain rule kind of situation, so yes. So that means we do not need to use logarithmic differentiation. Basically, that's the rule. If we can find it by some other means, we would do so. All right, so going to the next one now. Now to the y equals x to the 4th. Would we need logarithmic differentiation for that one? Nope. It's just power rule. And so, don't need it for that one. How about our e to the power of x squared? Nope, because it's e to the power of x squared. And I do know what e to the power of x's derivative is. That would just be e to the power of x. So this would be a chain rule with that, and you'd be good to go. What about for this next one? Would we need chain rule for this? Not chain rule. Logarithmic differentiation for this one. I've seen some of you shaking your heads, and yet it looks a lot like one where we would need it. Now I'm going to come back and look at the details on that in a moment here. Let's take a look at that last one. Would we need logarithmic differentiation for the last one? For this last one, we will need to use logarithmic differentiation in order to be able to do that. Now, the reason is, what's similar about these two where we did that and did need, in fact, logarithmic differentiation, is that you notice that in both of these we have x both in our base and in our exponent. And so then, taking a look then, I said I was going to come back to this one. Would we need logarithmic differentiation there? Well, do we have x in both the base and in the exponent? And this one's a little bit trickier to look at, which is why I'm coming back and looking at it more closely, because we might well be looking at it and saying, well, yeah, there's an x down there and there's an x up there, so that's an x in the base and the exponent. But that's not quite true, because this x is the exponent, but what is the base of that exponent? The 2, not the sine of x. If it was sine of x to the x, yes, you would need logarithmic differentiation. But instead, this is actually just one where we would use product rule with those 2 separate pieces. So you wouldn't actually need to do the logarithmic differentiation of both sides there. Just kind of keep that out there. But the biggest thing that I want you to notice is that we do need to use logarithmic differentiation when the x is in both the base and the exponent. That's such an important point that it might be worth making note of to yourself and writing that down. All right, so now that we've seen when we need to use it, now let's actually do it with one of those that you were just seeing on that list where, yes, we do need logarithmic differentiation because, see, we got the x in the base and in the exponent. So please actually take the derivative of this equation. All right, so for finding this derivative, this is one of those logarithmic differentiation ones, so that means we have to start by taking the log of both sides, and yes, we want to do natural log, so we're going to do natural log of both sides. And remember that the whole reason why we do natural log of both sides is because a logarithm allows me to take the exponent and pull it out. And so then this is going to become the natural log of y equals cosine of x times the natural log of x. Now you no longer have an x both in your exponent and in your base, which means now you can find your derivative by other means. And so when we go to find this derivative, we're doing it implicitly. We're going to be doing the derivative of natural log of y, which is going to give you 1 over y times y prime, or y prime over y if you simplify it as you go. Either way is fine. And then on the right side here, we got to use product rule. So original times the derivative plus the derivative times the original. And then from here, all we really have left is just clean up and tidying it any way that we can. So I'm going to go ahead and multiply both sides by y so that I have y prime by itself. And on the inside there, it looks like I can do a little bit of cleanup. Instead of cosine of x times 1 over x, I could just make that cosine of x over x. And instead of plus and negative, we can make that into a subtraction. That's about all the cleanup that we can do in there. All right, there is one last step, though, that I'm going to go through. Because it's very easy here to replace that y with something just in terms of x. Because remember, we're told up here what y equals. We're told that x equals x to the power of cosine of x. And so our last step is we're going to plug that in for y. So we're going to make this actually x to the power of cosine of x, and then times the same thing. And we're done. And so continuing with our practice of these, I'd like you to now find the derivative of this equation. Now, one question you have to grapple with right away on this one is what's being squared. Am I squaring the x to the power of x? Or does this mean that I'm squaring the x that is in the exponent? When you see it written like this, where there's no parentheses put in, you go ahead and assume that the squared is attached to whatever it's right next to, which is just the x. So if we were putting in parentheses to clarify, this is where they would be. Proceed from there, please. All right, so with this one, we know we need to use logarithmic differentiation because, again, we have an x in our base and an x in our exponent. And so I start by taking the natural log of both sides. So that's going to give me the natural log of y equals, and I'm going to jump over a step here and just go straight to the fact that I know that's going to give me x squared times the natural log of x. All right, now that we are here, we can go ahead and find our derivative. So that's going to give me y prime over y, again because it's 1 over y times y prime. And then I'm going to be using product rule here on the right side. So original times the derivative plus the derivative times the original. Now we solve it for y prime. So we go y prime equals, and then we multiply the y to both sides. Yes, I go ahead and write it in as a step. That way I don't lose track about where this magical thing changed in there, where the y went. And I can simplify a little bit. Y squared times x squared times 1 over x would give me x. So this is going to be x plus 2x times the natural log of x. And then finally replace the y on the right side with what y equals, which is the x to the power of x squared. Otherwise, everything in the parentheses is the same because we already simplified it as much as it could go.